fourth segment of in situ permeable reactive barriers. We've been talking about some examples of treating petroleum hydrocarbon and mixed plumes. We're going to carry that on here. We want to talk about something called a trenching gate. That's treating BTEX, and it's doing so with a minimal air sparging, again emphasizing the bio as the removal process. The study was conducted with researchers from the University of Calgary at a gas plant in Western Canada. Geology and the setup of the trenching gate is illustrated here. The area is underlined by silt sandstone bedrock. There is a silty shale that is weathered, and it forms a regolith, which is a mixture of the overlying glacial material and the weathered bedrock. Above that are clayey, silty tills, which are very low permeability. But there's also a cobbly till of variable permeability, often quite low, through which a plume is emanating, moving off-site from a gas plant. And that was the objective of the trenching gate, was to intercept and treat that plume. The gate is in the middle, and the trenches are on either side, spread out to capture the main plume heading off-site. Here's a cartoon layout of the trenching gate system. The source is ongoing leaks and spills in the gas plant. The idea was that that would be cleaned up upon decommissioning of the gas plant and not before. So they needed a way to treat contaminant plume for perhaps 20 to 40 years, the lifetime of the plant. The trenches are illustrated here. They're dug into the ground. They have a plastic backing on the down gradient side to prevent water from moving through the trench. They have pipe in it, perforated pipe, and that's the main way of moving water along the trench to the gate. The trench is also backfilled with very permeable gravel to enhance the transport down to the gate. The site engineer is there for scale. The gates, three of which were used, are culverts. These are used in construction, putting roads over streams. This allows the stream to pass underneath. It's galvanized metal, so it's quite resistant to weathering and erosion. These are attached to the pipes coming out of the trench and also then attached to each other by pipes. One of the problems with trenching gate is that you have to get the water back in the low permeability material at least as rapidly as you get it out, or you'll be plugging the system up from the back end. To do that, a series of trenches was put in the down gradient side that gave us about 1.5 times the surface area for release of water as we had for collection of water. Again, the challenge is to design, and one of the important criteria is the concentration of groundwater coming in. In this case, the consultants took a fairly conservative approach by taking the maximum concentration they found on site. It was about 12 milligrams per liter of BTEX. Now, many piezometers on site had much lower concentrations, so this really was a conservative approach. Again, they installed 3 gates. It turned out that one of those culvert gates was sufficient for adequate treatment because, again, the input concentrations were much lower than the design level. But having 3 gates instead of 1 was a relatively minor cost. Minimal air sparging, really just providing enough air to enhance biodegradation, was sufficient, in fact, to maintain the effluent concentrations below the guideline levels. Now, in this case, we really did try to do minimal biosparging, but there really wasn't a concern about off-gas. The gas plant has an ambient air quality challenge, so that we weren't going to be a significant source of hydrocarbons in the immediate area around the plant. But in any event, we thought it was just good practice not to create more off-gas. This is the sparging. The system was turned on and off, and when it was on, you could see bubbles coming up to the surface. So it did a very good job of aerating the water in the culvert. Again, we used drip irrigation tubing for the sparging. Again, we wanted to create bubbles throughout the bottom of the culvert. Well, the plume control was quite straightforward. The question that was raised, what if the concentration had been as predicted, 10 plus milligrams per liter of BTEX? We were confident that a single gate and just sparging would not have been sufficient unless we actually deliberately created a large off-gas component of the treatment. So we conducted some research to see if the gate system was more challenged, how it would perform. Very interestingly, it turned out that phosphorus, not nitrogen, was a limiting nutrient. That is, once you provided enough oxygen, the system was now limited by phosphorus, and adding phosphorus would enhance biodegradation rates. We speculated that a lot of nitrogen-containing organic compounds are used in treating the natural gas to remove sulfur, and so we speculated that there was a background level of nitrogen in the system unusually high. In any event, the challenge was how to provide phosphorus in this funnel and gate. Again, you want a fairly passive way to do it. Well, the way we decided to do it was to combine a slow-release fertilizer that contained phosphate with the mineral apatite, a phosphate mineral, a relatively insoluble mineral, so that we would get an initial enhancement of the phosphate from the biophos, and then we'd have an ongoing low concentration of phosphorus coming in from apatite. And that seemed to overcome the phosphorus limitation. Well, once you solve the phosphorus limitation, then nitrogen becomes limiting. So how would we add nitrogen to this system? The nitrate briquettes won't work. That's adding nitrate as an electron acceptor. We want to add reduced nitrogen as a fertilizer. So in this case, since we had a sparging system already set up, we decided we would sparge periodically, about once a week, a small amount of ammonia gas into that system. That had a few more health and safety issues, but it was okayed, and we were able to do that. Again, some research aspects, we wanted to test our system and see if in fact it would handle higher concentrations. So we created higher concentrations in the funnel and gate. We took the natural gas condensate, the BTEX containing component, put it in a water truck, added groundwater from the site, drove the truck around to mix the two, and then stopped the truck beside our gate and allowed the two phases to separate. We then injected the water phase, or much of the water phase, into the first gate, where the sparging mixed it very thoroughly. So we then had a fairly constant source of BTEX containing groundwater at about 10 milligrams per liter, containing oxygen from the sparging, that went into the second caisson. The second caisson was divided in half. In one half, the solid phosphate sock was put in front of the inflow pipe, and ammonia gas was sparged into both sides. The effluent from that was then checked, and sure enough, in the effluent from the phosphorus side, we got essentially complete removal of the BTEX. The effluent from the non-phosphorus side had significant BTX levels still remaining. So we did demonstrate that if, for instance, higher concentrations were encountered later on, we had a way to treat it. So what were some of the lessons we learned? This idea of a trench to draw contaminated water into a localized treatment system seemed to be a very good idea, very workable in this situation. Remember that you have to design the effluent from the treatment system such that it doesn't become the blockage to the whole system. Air biosparging alone may not always be sufficient, especially at high organic loading. It was sufficient here. It's been operating for 15 years without any nutrient addition, and if it hadn't been sufficient though, perhaps adding nitrogen, phosphorus in some cases, or both, would be required, and we demonstrated that that was possible. It shows you the advantage of funnel and gates, trench and gates, permeable reactive barriers. It allows you to do a lot of manipulations that are sort of innovative and lots of fun. And again, the idea is to add nutrients or make any additions in a very passive manner. Operating costs really need to be minimized. So lastly, we want to talk about something very simple, shallow trenches. These have been used to treat petroleum hydrocarbons and nitrate. The idea is to create some reaction in a very shallow trench. Let's have a look at some systems and some optimizations done by people at Waterloo. So here's a picture of a Brazilian example. We have a very shallow trench cut. It intercepts the top of the water table. Its real design was to intercept free-phase L-NAPL. The trench ends up at an API separator and separates and collects the NAPL. There's very little NAPL present, and so one wonders if you actually have to have that water in the trench moving. Why not just a stagnant trench? The idea is you want the L-NAPL plus contaminated groundwater plume coming in to be cleaned. You can see in the area in the foreground in the trench, we see a lot of iron staining. That's because the BTX plume has consumed all the oxygen in the groundwater. This groundwater then, being anaerobic, is able to dissolve iron from minerals and creates a high concentration of iron 2+ in the water. Upon exposure to the atmosphere, that's oxidized and we get the precipitation of iron oxyhydroxides. So we do see some of the plume in this system. The idea would be to design a system that treated both a small amount of L-NAPL flowing in and also contaminated groundwater. What if the system had a deeper component? How would we intercept that deeper flow line? We can add oxygen to the trench, but we need to get that flow line into the trench in order to treat that flow line. We can dig a deeper trench. Digging deeper trenches is it's also geotechnically challenging in many cases. So you probably don't want to do that if you could avoid it. Concept being developed a few years ago at Waterloo was, would a wider trench do the job? Would it somehow draw up the deeper flow lines into the trench zone? Wider is easy to construct, so that's a good option, perhaps. So Dr. Robertson and his colleagues looked at this. They had a field site where they applied the technology. They were looking at a very shallow nitrate plume, and the idea was to see if they could create a shallow trench that would intercept the nitrate. In the trench they would have wood, which actually is a reductant. The aerobic activity degrading woody materials provides an anaerobic environment, and with an anaerobic environment denitrification occurs and the nitrate is removed. So they created a higher permeability trench and examined the treatment. The nitrate concentrations coming in were significant, the nitrate concentrations down gradient weren't. So it looked like it worked. What were the principles that we might gain from this for petroleum hydrocarbon treatment? Notice that they did capture deeper flow lines with this wide, shallow trench. So they used a simple numerical model to examine some optimizations they might do. And the real question is, can we intercept the deeper flow lines and therefore be able to treat them? One optimization they looked at was increasing the hydraulic conductivity contrast between the more permeable trench and the aquifer. And each time they increased the hydraulic conductivity, they did capture a deeper flow line. But they still only had about a 5-meter depth being captured in this sort of standard case. Not a terribly expensive way to do it, but it might have challenges. For instance, if you're working in a permeable sand, it might be difficult to get 1,000 times more permeable material into a trench. How about the thickness? Would a deeper trench intercept deeper flow lines? Pretty sure it would. And as we went deeper, 1 meter, 3 meters, deeper flow lines were intercepted. 3-meter deep trench was intercepting flow lines down to 5 or 6 meters. So that's good, but construct 3-meter deep trench is a geotechnical challenge in some cases, certainly a cost. What about simply a shallow but wider trench? So here's a trench 2 meters wide, 8 meters wide, 16 meters wide. Again, it's capturing deeper flow lines. In general, it's much easier to construct a wide, shallow trench than it is a narrow, deep trench. So this seems to be a very beneficial approach. So let's summarize that. The upper figure, we have the depth of capture with the hydraulic conductivity contrast between the trench and the aquifer. You can see that we get some advantage But at about a hydraulic conductivity contrast of 100, there's really no more advantage. And we're still capturing fairly shallow plumes. What about the thickness of the layer? Well, it turns out that you can, again, capture 3 or 4 meter deep plumes with a trench that's about half a meter thick. Going deeper is not terribly useful. So this is not really a big benefit, and again, it's challenging having a deeper trench. What about a wider trench? Well, again, we seem to capture deep flow lines quite well, and we haven't yet reached the maximum depth of capture. But it looks like we still have a room to capture perhaps an 8 meter deep flow line. And again, I think the shallow, wide trench is the most economical. So the advice is to go wide, not deep. That seems to be the case to go for. So in many cases, as you are looking at shallow petroleum hydrocarbon contaminated plumes, think of a simple trench with perhaps an aeration system in it, or simply exposure to the air may be sufficient for enhanced biodegradation. What I hope you're taking away from these case histories is that you have a lot of room for innovation within permeable reactive barriers. Where is the future going? Well, I'm not really sure it's your future, but here are some ideas. The main issues with permeable reactive barriers are treatability of contaminants. We have plumes that require a number of different treatment systems to get rid of all the contaminants. Some chemicals, MTBE for example, seems to be rather recalcitrant to almost all treatments. We need some innovation in treatments. Constructability. Again, the prize is for low-cost construction, simple, robust systems. And as long as we're considering life cycle costs, PRBs often do very well. Now, the problem with PRBs is much of the expense is up front in the construction phase, so they need to last a long time before the life cycle cost gets lower than a system like pump and treat, which has as its main cost the operational phase. What are some of the other future things I think we're going to be looking for? Well, I think the recognition that the permeable reactive barrier doesn't have to be the only treatment is an important one. Remember, what we're trying to do is combine natural degradation with any treatment to obtain the desired result. So don't worry if the PRB can't treat everything, as long as nature can polish it off. Better treatments. Zero-valent iron is good for some contaminants. Bimetal material is better. And there's a lot of interest these days in nano iron. In many cases, what we're doing is incorporating or borrowing wastewater treatment technologies and experience. So make sure you stay up with the literature or with your friends in wastewater and see what techniques they're developing. We demonstrated one sequential PRB, and I think there's going to be a lot more of those. Again, with contaminants not being easily treated by one technology, we do need multiple treatment technologies. An interesting area at the moment is persulfate in situ chemical oxidation. The product of persulfate, which oxidizes many hydrocarbons, for example, is sulfate. So we end up with a plume of sulfate and any residual contaminants. Perhaps sulfate-reducing bacteria can be encouraged to use that sulfate to degrade the residual contaminants. Installation methods. Prime costs are construction. Simpler, easier methods are always welcome. You notice that all the case histories we've discussed are in porous media. Fractured bedrock is very difficult. High construction costs, really challenging. And of course, as the plumes get deeper, the cost of all that construction rises probably exponentially. So those are areas that we need to improve. As well, we need to improve our ability to predict performance. Part of that is experience. We need more experience and more demonstration of how these things work, but we also need better models, both conceptual and numerical, to allow us to take those experiences into design in the future. And it's your future, and I think PRBs are a significant aspect of contaminant groundwater remediation. Thank you again.